This video we're looking at approximations and error. To start off with, we're looking at errors in measurement. So when we take a measurement, we are usually reading some sort of scale. We approximate the length by recording to the nearest mark. In doing so, our answer may be inaccurate by up to half a unit. So a measurement is accurate to plus or minus half of the smallest division on the scale. Quick example of what that means. If x equals 3.24 centimetres, then the unrounded value of x is somewhere in the interval of 3.235 and 3.245. So we call that the lower bound, being 3.235, and the upper bound, 3.245. Now you'll notice here in the notation, we just have a greater than or equal to sign here and just a less than here, because with that 3.245, if that was also an equal to, we would be rounding up because of the 5. So it's only going up to that value, which is why it's like that. First example, the height of a tree is recorded as 4.75 metres, corrected 2 decimal places. Write the interval within which the exact height of the tree is found. So we've recorded it as 4.75, but what is the interval that tree could actually be between? So let's look at our upper bound. So our upper bound is what's the highest value it could have possibly been, which would be 4.75, and we add another 5 to the end of that, because that's the upper bound, that's where it could have gone up to. Then the lower bound would be 4.7. Now, to get to 5, to round to 5, we have to minus 0.005, because we could have got 4.745 is the lowest value that would round to 4.75 to 2 decimal places. So they're the two bounds that this tree could have actually been between. And when we write the interval, we put the lower bound, the 4.745, less than or equal to, because that does round to the 4.75. And then we only go to a less than 4.755, because that includes everything up to 4.755. Example 2, the volume of a soda can is measured to be 334 ml to the nearest milliliter. Determine the upper and lower bounds of the volume. So let's look at the upper first. So the upper, we've got 334. So what we're going to do, we're going to add on half a unit here. So that would be, we're just going to put in a 0.5. Because it's up to that would still round to 334. Then the lower bound, it will be 333.5, because that would round up to 334. So that would be our upper and lower bounds. And it doesn't tell us to write it in interval notation here, but I would still always write that, because it just covers you just in case that's what the mark scheme is wanting, but you're not too sure. Example 3, the length of a rectangular flag is 27.5 centimetres and the width is 16.8. Both measurements are given to the nearest millimetre. Determine the upper and lower bounds for the area of this flag. Give your answer correct to 1 decimal place. So we need to look at each dimension separately first. So for the length, what are the bounds this could be between? So the length was 27.5, which means it could have been 27.45 all the way up to 27.55. Anything between that range would round to 27.5. Then we want to do the same with the width. So the width was 16.8, which means the lower bound would have been at 16.75. So you add a decimal place to what you've got there, and then you do your adjustments there. Width all the way up to 16.85. So anything between those two values would round to the 16.8. On the upper and lower bounds for the area. So what we need to do for this is we need to take the two lower values, because that will give the smallest possible area, and the two larger values will give the largest possible area. So we have to find both of those. So the minimum area could have been 27.45 multiplied by 16.75. The two smallest dimensions of the length and the width, which gives a 459.7875 area. Now the maximum area is found by multiplying the two largest possible values, which is 27.55 and 16.85. And that gives an answer of 464.2175 centimetres squared. So the area could ultimately have been between these two bounds. Now it says determine the upper and lower bounds. So this one will be the lower bound and to 1 decimal place. So the lower bound could have been 459.8 to 1 decimal place. And the upper bound was 464.2 centimetres squared to 1 decimal place. Example 4. The length of a rectangular field is measured to be 112 metres and the area is found to be 8,630 metres squared. Both of these measurements are given correct to the nearest metre. Find the upper and lower bounds of the width. So a bit similar to the last question, but just a little bit in reverse. So first of all, let's look at our bounds. So the length, being 112, could have been between 111.5 and 112.5. And then the area could have been between 8,629.5 and 8,630.5. Right, so now we've got both those bounds there. Now to find the width, remember area equals length times width, so the width would equal area divided by length. Now to find the upper bound, so the maximum possible area, to do that we would need to divide the largest area, so 8630.5, by the smallest length. That is going to give us our biggest possible width. Our largest area divided by our smallest length. So sometimes you just have to think what's going to give me the largest and smallest. So in that case, our maximum width, our upper bound of our width would be 77.4 to 1 decimal place. Now the lower bound of our width would be the smallest area divided by the largest length. That's going to give us our smallest possible width, which ends up being 76.7 to 1 decimal place. So there would be our two bounds. Rounding off to significant figures. In the IB, if it doesn't state how it wants an answer to be rounded, you are expected to round to 3 significant figures. With significant figures, the first significant figure of a number is the first non-zero digit. Every digit after that is then classed as a significant figure too. Some examples here. Round the first one, 3.461 to 2 significant figures. The 3 is the first non-zero digit, so that's significant, and we want 2 significant figures, so it would be 3 point. Now the 4 is significant, that's our second significant figure, but we have to round it up to 5 due to the 6 afterwards, so it would be 3.5. B, we have 0.00724. Now the first 3 zeros are not classed as significant. We still need to write them in our answer, 0.00, but this 7 is our first non-zero number which is significant, so it'll be 7, and then our next number will be 2, and we leave it at that. 708 to 1 significant figure, so our 7 is our significant figure. The other two are not, but obviously it's 708, so we still have to write the 700, we can't just write 7. 20.158 to 3 significant figures, so the 2 significant, the 0 significant, we have point, and the 1 is significant, which we then have to round up to 2, because the fourth number is a 5. Note here, as I said, in an IB exam, if it's not specified, always give the exact answer first, then round to 3 significant figures. So on with some more on approximations and error, absolute and percentage error, which comes up a fair bit in an IB exam. Whenever we measure a quantity, there is almost always a difference between our measurement and the actual value. This is called the error. So the size of magnitude of the error is called the absolute error, and it's always positive. And what makes it always positive is these straight lines either side of the equation. So absolute error equals the approximate minus the exact. And you see those two straight lines here? That means the absolute value, which means the answer is always positive, whether we do get a positive or a negative value. Error is often expressed as a percentage, and our percentage error equation is the approximate minus the exact all divided by the exact. We take the positive value of that because we have the straight lines either side, the absolute value, and then we times it by 100. So just a quick example so you can see how it works. So you estimate a fence's length to be 70 metres, the true length is 78.3 metres, find the absolute error. So the absolute error, if we look back at our formula, the absolute value of the approximate, which is 70, minus the exact, which is 78.3. When we do this, we'll have the absolute value, which is negative 8.3. Now, because we have the straight lines next to it, it means the error is just 8.3 metres. Our percentage error equals the approximate minus the exact, all divided by the exact, which is 78.3, and then we times by 100. And take the absolute value, you end up with 10.6%. Next example, the two shorter sides of a right angled triangle are measured to be 3.1 centimetres and 3.9 centimetres. First of all, calculate the estimated length of the hypotenuse. When we're calculating an estimated length, we just think about how could I work this out if I didn't have a calculator? And it would be to round the 3.1 to 3 and the 3.9 to 4. That is able to give me an estimation, okay? And if we do this, we'll end up with 25, so x will equal 5. So that is an estimated length of the hypotenuse based on the other two sides being 3.1 and 3.9. Say if I didn't have a calculator, that's what I'd do. Now part B, find the value of the length of the hypotenuse correct to three significant figures. So now because we have a calculator, what is the length of that hypotenuse? So it would be 3.1 squared plus 3.9 squared. X squared then equals 24.82. And so x equals 4.98 to three significant figures. Now remember, we always write our answer to three significant figures. C, calculate the percentage error. So now we have our estimated and our actual, so we can put these into the equation. So our percentage error would equal the absolute value of the estimated minus the actual divided by 4.98 times by 100. Now remember, when we're putting this into our calculators, we're not using 4.98, we are using the whole number from our calculators from part B, not the rounded number. We can use a rounded number in our writing, but in our calculators, we use the actual value. And that gives us a percentage error of 0.361955, which is equal to 0.362% to three significant figures. And final example. Alan wants to lay carpet on his 4.2 metres by 5.1 metre lounge room floor. He estimates the area of the lounge room by rounding each measurement to the nearest metre. A, find Alan's estimate to the lounge room area. Alan estimates by rounding each measurement to the nearest metre, so he is actually doing 4 metres and 5 metres, which means he's going to estimate the area as 4 times by 5, which is 20 metres squared. Part B. The carpet costs $39 per square metre. Find the cost of the carpet using Alan's estimate of the area. So nice and easy, the cost will be $39 per metre squared, and he's got 20 metres squared, so it's 39 times by 20, which will be $780. Part C wants us to find the actual area of Alan's lounge room. So the actual area will be the 4.2 multiplied by the 5.1, which is 21.42 metres squared. Part D, find the percentage error in Alan's estimation. As the percentage error equals the absolute value of the approximate, which was 20, minus the exact, which is 21.42, divided by the exact, and then we times that by 100. And when we do that, we get it is approximately 6.63%. Now, will Alan have enough carpet to cover his lounge room? How should he have rounded his measurements? So Alan has only 20 metres squared of carpet. So he doesn't have enough because the actual area is 21.42 metres squares. So in this situation, he should have rounded up to make sure he had enough carpet. And you just need to write that in some type of sentence.